Friends, in the last class, we did discuss some of the aspect of open channel flow, and today we will continue from that. Let us just recapitulate what we did in the last class. Well, first we did discuss what are the differences between open channel flow and the pipe flow, and that we will try to understand some of the details of open channel flow, and then we studied some of the important geometric parameters that we normally use in various work of our open channel flow. Well, then we went to classification of open channel. Well, that was classification of open channel and not the classification of open channel flow. Well, today we will start with that is classification of open channel flow. Well, now when we say that classification of open channel flow, that we can do on different basis and based on say different criteria we can classify open channel flow. So, these are some of the criteria you can see that say we can classify open channel flow based on variation of flow parameters with time, variation of flow parameters with time. Then we can classify it on the basis of variation of flow parameters with space. Well, by space here we mean that the flow parameter, well, first let me go to what is flow parameter. So, when we say that variation of flow, then we need to just see that what are the things basically varying within the flow, and that is why we decide or we talk about some parameter like that flow velocity or say flow depth or say flow discharge, volume of flow that is moving through a channel. Now, how these things are changing with respect to time and with respect to space? Well, by space we means that distance, say at a particular section we have some velocity or depth, at a downstream section we will be having some other velocity or depth, and that way how it is changing. Well, based on those things we classify open channel flow. Well, then we talk about classification based on turbulence. Well, you can see that the flow in nature sometimes it moved in a very turbulent way and sometimes it is in a very smooth way. That we did we have already seen that in our very introductory class of our open channel, that how the flow can in different forms are moving in a different way. So, based on how much turbulent or the strength of turbulence in the flow, we classify that open channel flow. Then again, based on concept of critical flow. Well, for understanding this particular point, that is the critical flow, we need to discuss something more that we will be doing, but there is another classification what I want to mean, that which we do based on the critical flow. Then again, we classify flow based on conceptualizing the flow as 1D, 2D or 3D. Well, conceptualizing the flow means for our various computational work, we many a time just assume that the flow in the river is one dimensional. By one dimensional we mean that it is moving in a particular direction. It is not, it does not have any velocity in the lateral direction or in the vertical direction, there is no change. So, like that when we consider, then it is one dimensional, sometimes we consider it is two dimensional. Okay. So, based on this one dimensional, two dimensional, three dimensional also we classify the open channel flow. Now, let me go into each of this classification in a more detailed way. Well, first we are talking about classification based on variation of flow with time, and that classification we do as steady flow and unsteady flow. Let me take the pen here. Well, steady flow, by steady flow what we mean, that is when the flow parameters at a section do not varies with time, then we call this as a steady flow. So, this part is important. The flow parameter at a particular section do not varies with time, that we call as a steady flow. And then mathematically we can represent that as, say, del V del T is equal to 0. Now, why it is del V del T or say del Y del T? What is V? V stands for velocity and Y is, say, depth, Q is discharge. Well, now one of the flow parameters, say velocity, when we say velocity, it can vary actually with respect to space, that I am writing as, say, x, and it can vary with respect to time. Now, when we say the variation of velocity, then probably we would have written it as dv, that is the variation of velocity. Well, this dv, that is the total variation of velocity when we say, and this in fact is varying with both space and time. Now, when we say that it is varying with space and time, that means total variation is partially with respect to time and partially with respect to space. So, when we say that variation of velocity with respect to time, then we write as, say, partial variation of velocity with respect to time. And then when we write that del V del T is equal to 0, so del V del T is equal to 0 means partial variation of velocity with respect to time is equal to 0, means it is not varying at all. It is not varying at all with respect to time, but with respect to space it can vary. Well, then similarly del Y del T is equal to 0 means the depth is not varying with time. Well, but it can vary with space, then it is not varying with discharge. So, this is what we call as a steady flow. And then what is unsteady flow? So, unsteady flow is that when the flow parameters at a section varies with time. That means, at a particular section when we are observing a flow, then we find that at one time we have some depth, at the next time we might be having some other depth. Well, so that mathematically we can write that del V del T equal to Z is not equal to 0 and del Y del T is not equal to 0 or del Q del T is not equal to 0, right. Well, say when we talk about steady flow, suppose this is the channel section, sorry, this is the bed of the channel, and then we have a flow like this. When we say it is steady, that means at time equal to, say, t1, at time equal to t1, suppose we are finding it like that, and that we talk about a particular section. In this section, suppose the depth at time equal to t1 is this much, y1. This depth will continue or this depth will remain the same at time equal to t2 or whatever may be the time at time equal to any time tn. However, suppose here the depth is y1, here the depth can be something else, say y2. It is not necessary that here it is y1, here also it will have to be y1. It is not like that. But this sort of flow we call as a steady flow, and it can be like this also. That means this is bed, so it can be like this also. There is no harm. That means if it is rising, changing, here it is y1, here it is y2, but with time, at any time, that is t equal to t1, t2, t3, tn, at any time it is remaining like that, then we call this as a steady flow. Well, then what is unsteady flow? Say in the channel we are finding that at time equal to t1 it is here, and time equal to t2, say another time we are having that flow is like this, t2, then this sort of flow we refer as unsteady flow. Well, let me give you one example, practical field example. Suppose this you have a dam, say this is one dam, you can refer to the slide, this is a dam, and you have some water stored behind the dam, and this is the bed, Okay. So, suppose due to some reason suddenly the dam has failed, then the water will start flowing in this line, okay. Now, you can see, say at time equal to 0, the water is standing like this, and at a time later period, say it is at 1200 seconds, suppose the dam has failed, so it is no more there, water has got released like this and it is in this point. So, if you take any section, suppose if I am taking any section here or even here, then you are finding that at time equal to 1200 second we have depth here this much, but you just see that in the next moment this is changing like that, in the next moment it is changing like that, in the next moment it is changing. So, that way when this sort of flow are changing in a practical situation, then we can call this as unsteady flow. Then let me come to another classification, that is classification based on variation of flow with space, and that we can classify in the form as uniform flow and non-uniform flow. Well, what is mean by uniform flow, what is mean by non-uniform flow, that we can see, that is the uniform flow when the flow parameters in a channel reach, means in a portion of the channel, when the flow parameters in a channel reach do not varies with space, and again that is mathematically we can write, say del V del x, del y del x, or del q del x is equal to 0. So, here we are looking into the variation, partial variation of velocity with respect to say distance, or partial variation of depth with respect to this, a partial variation of all the flow parameter we are looking in terms of distance, and that way we are just observing whether it is changing, and when it is not changing, that means we are referring this as uniform flow. Then we can have, when we have uniform flow, we can have non-uniform flow as well, and here the flow parameters in a channel reach varies with space, and mathematically that we can write as del V del x is not equal to 0, del y del x is not equal to 0, and similarly del q del x is not equal to 0. Well, now here again we need to draw some figures to illustrate what we mean by that. Well, then say uniform flow means, if I consider this as the channel bed, well, depth of flow is say this one, and here in a section 1, suppose we have depth equal to y1, then at the downstream section 2 our depth is not changing, this is also remaining as y1, that means the depth is not changing. Well, discharge, what is coming is suppose q, then we know that q is equal to area into the velocity. This is very well known relation, continuity condition we call. So, suppose if q is coming, if it is a rectangular channel, or whatever may be the channel shape, suppose if it is a prismatic channel, everywhere the channel is remaining same all along these things, then when we have depth y, then here velocity v, if I say that this width is b, then we can write that q is equal to area means b into the y. So, q is equal to b into y into v, velocity. So, when our q, the same amount of discharge is coming, so discharge is not changing all through the channel, or depth is not changing all through the channel, it is here y1, here also it is y1. So, b, if it is a prismatic channel, b is also not changing, and then so v will not change, that means here if it is v1, here also it is going out with a velocity v1, and this sort of flow we call as uniform flow, that is the flow parameters are not changing with distance. with space. Okay. Now, if we can have a flow of this kind, that say this is flow, here the flow parameters, here is y1, here it will be y2. So, the flow parameters are changing. If the same amount of discharge is coming, then suppose no discharge are entering into this channel portion from this side or from laterally, then this will continue to move, and then velocity here will be v1, but velocity here will be v2, a different velocity will be getting, because the depth is changing, that is the sectional area is changing. So, you will be getting a different flow velocity. So, this sort of flow we refer as, say, non-uniform flow, non-uniform flow. So, we have seen that we can have uniform flow as well as we can have non-uniform flow, and in practical situation where we can have this sort of non-uniform flow, suppose we have a channel like this, and then you are putting some small dam or say barrage like this, and you are obstructing the flow. So, earlier suppose the flow depth was in this level. Now, when we are putting obstruction here, then the flow depth will gradually rise like this, and then when it crosses this point, then it will be flowing this way. Okay, downstream something is happening, we are not very much concerned about that right now. And well, so this flow, but it will continue like this, it will continue like this, and that flow is changing with space, and that is why this sort of flow we refer as non-uniform flow. Similarly, a channel section is there, and suppose there is a drop like this, and then flow is coming from this side, it will be falling like this, it will be falling like this, and then this surface is also a non-uniform flow which is changing with space. Here it is y1, here it will be y2, different. So, like that we can have uniform flow and non-uniform flow. Well, now when we name this flow, say whether we can call a particular flow as steady flow, whether it will be sufficient, or if we say that particular flow is a uniform flow, will it really represent what the flow is? Definitely not, because when we are talking in terms of variation, we need to say how it is behaving, so far its variation is concerned with respect to space as well as time. So, in that case we classify this by mentioning the combination of whether it is steady uniform, whether it is steady non-uniform, and like that. Well, so as combination what we can have, say we can have a steady uniform, a steady uniform flow. Well, then what we mean by steady uniform flow, that is, say it is a uniform flow, it is a uniform flow, that is the depth here as well as depth here is same, velocity is as well same, and this is continuing for any time, say t1, t2, whatever it is, for any time tn, for any time this is remaining like that. So, as such it is not changing with time nor it is changing with space. So, we call this as a steady uniform flow. Well, then we can have in principle we can have unsteady uniform flow, but one point is true, that in nature we can hardly get a unsteady uniform flow, because if it is to be unsteady uniform flow, then what is that? Say you have uniform flow here at time equal to t1, say here it is y1, here it is y1, that is it is not changing with it is y1 again, right. So, it is not changing with space in a particular time at any instant of time t1, it is like that. Then if it is to be unsteady, that means in the next moment time t2 you will have to have another change, that is with time it is changing. Say at t2 you are having depth something else, say y2, at time t you are having something else y2. But in reality or in real field, that sort of flow, that is at this instant of time it is like this and then it is jumping to t2 like that, it is not practically possible. So, we do not get this unsteady uniform flow in nature. Well, then we can have, say, if we just see that is steady non-uniform flow, steady non-uniform flow, steady non-uniform flow, that already I have given one example, that suppose you have a barrier here, then the flow is rising like this and this is a non-uniform flow, this is a non-uniform flow and this is remaining like this for any time at t equal to say t1, t2, any time tn, this is not changing. So, as such it is steady, but it is changing with space, it is changing with space, here it is y1, here it is y2. So, it is called steady non-uniform flow. And say when we talk about unsteady non-uniform flow, unsteady non-uniform flow, that already one example I have given, non-uniform flow. Well, then we can see that suppose this is dam, what I gave one example, and somehow it has breached. So, earlier the flow water level was like this and then at time equal when it is failing, so water is moving like this. So, at time equal to t1 it is at this level, water level is like this. Well, and it is also varying with space, with distance it is varying, here depth is different, here depth is different. Then at the next moment at another time t2, this is again changing. So, but depth is also changing, depth is also changing with distance as well as it is changing with time, as well as it is changing with time. So, when the flow are changing with time at t3 it may be coming here. So, with time as well as with space this is changing, then we call this as a unsteady non-uniform flow. Well, so when we name a particular flow, we need to specify it in terms of whether it is steady uniform, whether it is steady non-uniform, whether it is unsteady uniform flow. Well, then again when we say non-uniform flow, well, more details of this non-uniform flow we will be discussing in a later chapter or in a later topic. But here I will just give brief about this, that classification of non-uniform flow. This non-uniform flow again you can classify in a way that it is gradually varied flow, then it can be rapidly varied flow, then it can be spatially varied flow. Well, by gradually varied flow what we mean, by rapidly varied flow what we mean, let us just see. Gradually varied flow means that flow is varying gradually. Again I am taking the same example, say we are providing a barrier, and flow is varying like this. So, this variation is gradual in a sense that this change in depth y1 and y2, change in depth y1 and y2 is taking place in a long reach. This reach is very long, and then so slowly or gradually it is changing, and this sort of flow we call as gradually varied flow. In fact, if you just in practical case when you see this sort of flow, you will not be able to just realize by just seeing the flow that there is a change in the flow depth. You will not be able to just realize, but the depth is changing. Well, some more technical aspect of gradually varied flows are there, and that will be coming when we will be discussing it in the under the non-uniform flow chapter. Well, Then, well, some example already I have given. When it is a drop like this, then also there can be non-uniform flow like this, and this is a curve which is coming down, but this is a curve which is going up. So, there can be positive curve going up, then there can be drawdown curve like this. So, all this sort of different type of gradually varied flow we can have. Then rapidly varied flow. Well, then rapidly varied flow means, say we have a channel like this, and then in normal conditions, say the water depth, if we allow to flow the water amount of discharge Q in this channel in a normal condition, suppose this is the flow depth, okay, this is the flow depth. Then if we put one gate, here like this, and if we make a small opening here, then what will happen, that this flow is emerging with a very high velocity at this point, because earlier it for moving this much of discharge, it need this much of height, depth of flow, cross sectional area, if we say in this term like that. But now you are keeping a small opening here, so it is moving with a high velocity, and ultimately on the downstream side it would try to flow in this level only. So, from here to here there will be a just jump like this, water will be jumping from this level to that level, and that phenomenon is called hydraulic jump. This phenomenon is called hydraulic jump. Well, now this sort of changes or this sort of flow we term as rapidly varied flow. Why rapidly? But rapidly does not mean that in a very short time it is varying. This is basically not related to the time factor. What it means, that in a very short reach it is changing. This length of this portion is very small. When we were talking about the gradually varied flow, the variation may say change of flow depth from one value to another value may be say in kilometers, I mean distance. But here it will be in say meters, it will be say 10 meter, 20 meter, something like this, it will be say 20 meter, 10 meter like that. And when you talk about gradually varied flow, suppose you are giving a barrier and then you are having this thing in nature, I am talking about, in practical field, say it can be of say 6 kilometer, 5 kilometer, in that range. Well, in laboratory channel we can form this in a very small length also, and that will be, of course, the dimension will be very small, and of course this distance what I am talking about, this will depend upon what is the height of this barrier, what amount of flow is coming, all these are dependent, but just a typical value I am just trying to give you so that you can appreciate what is the difference between this rapidly varied flow and gradually varied flow. And of course some other details are there. So for energy conservation in this portion, what is happening to the energy, what is happening to the energy in this gradually varied flow, what sort of equation we can write for this rapidly varied flow, what sort of equation we can write for this gradually varied flow, there are a lot of differences. So we need to handle this sort of flow in a different way. Then we talk about another type of variation that we call as a spatially varied flow. Spatially varied flow. Well, in a river system we can always find, or we see that a river is flowing like this, then some tributaries are joining, some branches are coming like this, and that sort of things is very common, and this is what we normally get. And in this sort of situation, suppose if I draw it like this, a channel is moving like this, it is carrying a discharge Q1. Well, then another channel from this side is joining this one, and it is carrying a discharge Q2, and then this is moving like that. So here in this section the discharge is Q1, you have some depth, and then when going to this downstream section, here the discharge will be say Q1 plus Q2, discharge will be Q1 plus Q2. So that way the discharge, one of the flow parameter what we are just observing straightway here, that is the Q1 discharge, this is definitely changing with space. So, it is a non-uniform flow, and then some discharge can go out also from this part, say Q3 is going out, then what will be the discharge here at this point? It will be say Q1, if I see beyond this one, it will be Q1 plus Q2 minus Q3. So, this sort of flow we term as spatially varied flow, and then when we treat mathematically all this different type of flow, gradually varied flow, rapidly varied flow, spatially varied flow, we treat all these in a different way. Some speciality are there. So, till now what we have said or what we have discussed is that how we can classify open channel flow in terms of or on the basis of its variation with time and space. Well, but some more classification we can do based on some other criteria. That is, initially I told that turbulence, this is one of the important issues. There is the classification based on turbulence. You can see here I am keeping some of the picture taken a different part. Here the flow is moving in this direction, and you can see that the flow is quite smooth. You do not find much undulation here, and then in this figure you are finding the flow is moving in this direction and flow has some undulation. It has started, I mean the surface is becoming a little bit undulated, and then it is moving in this direction. Then here you can see, of course, it is I mean it may not be that much visible, but from the terrain or from the entire geometry you can see that there is lot of turbulence in this flow, because lot of undulations are there and the flow is moving in a much turbulent way. And so the turbulence level in this and this flow is different, and then based on this turbulence we classify the flow in three classes that we call as a laminar flow, turbulent flow, and in between this laminar and turbulent, this is referred as transition flow, transition between turbulent and laminar. Now, what we mean by laminar flow? Well, basically when the water is flowing in a channel with a very low velocity, then for an ideal fluid we can see that it is moving well, rather than let me draw a diagram here. Say this is the bed, then we can see that supposed total depth of flow is this much, and if it is flowing with a very low velocity, then we can see that, or rather we can assume that the flow are moving in layer. Entire flow is definitely not moving with the same velocity. There may be difference in velocity, there will be difference in velocity between this layer and that layer, and we assume that flow are moving in layers, different layers of flow are moving, and one layer gliding over the other layer. And these streamlines, if we call this as a streamline, you know from your basics of fluid mechanics that what is streamline. So these streamlines are parallel, and then if I draw a velocity diagram, that is what I mean by velocity diagram. If I draw a graph here, say what will be the velocity here, say velocity here is this much, and what will be the velocity here at the bed, when it is just in touch with the bed, it will, the fluid which is just in touch with the bed may not be moving at all. So this part we can say that velocity is 0, and from here to here velocity is changing gradually. Well, how this change in velocity occur, that we will be discussing in the next class, but here just I am trying to show you that the velocity variation is like that. You can find a high velocity here and then low velocity here, and gradually it is coming down, and at the bed it is almost 0. So that sort of velocity variation we get in case of laminar flow. Well, then in turbulent flow what is happening? Well, let me draw here in turbulent flow. If this is the bed, then the streamlines or the flow layer are not moving smoothly like this. Say one streamline is moving like that, another is moving like that. If the total depth is this much, then in between these flow are getting mixed up, this flow are getting mixed up like this. So increase in turbulence means mixing up of flow. Say a particular water particle remaining here, next moment it may reach this point. Like that, when we draw the velocity diagram, what will happen to it? Now we cannot say that these are moving in layer. So what you have, you might be having some velocity here at this moment, the same particle is moving to the lower side with high velocity, so there is a mix up, and this was moving with a low velocity, then this particle will be moving to upper side, means its velocity, it is gaining its velocity again. So like that, velocity become more or less uniform in the intersection except the small portion near the bed, and in other part the velocity become almost uniform. So that way in turbulent flow the velocity variation along the depth become almost uniform like that. Well, and then between these two, laminar and turbulent flow, we call it as a transition flow. Well, then as I am telling, probably you might be thinking, okay, what is transition flow? Laminar is this, understood clearly. Turbulent is this one, when there is a mixing up of the flow. And then what is transition? That of course, to define very specifically, we must take help of some index, and that index generally we used, or it is used, is Reynolds number. You know very well what is Reynolds number. So that Reynolds number we express as rho VL by mu. So rho is the density of flow, this is the density of fluid, then V is velocity. Now what is velocity? That is again a confusing term, because already in the last slide itself I have shown that velocity is varying like this. Here it is like that, and then here it is like that. Then this velocity is what? Well, we are talking about, when we just put a velocity term here, we are meaning that this is the average velocity. So this velocity we call, rather than writing it as velocity, we can write it as average velocity. You can write it as average velocity. So this is average velocity. Okay. Then this L is characteristic length. So this L represent a length term. And based on the problem, which length term is significant, that way we take this length term. Say for a pipe, we consider this length term to be the diameter of the pipe, when we just talk about the Reynolds number of a pipe. And in open channel flow, we take this length term as either hydraulic radius R or hydraulic depth D. In the last class itself we did discuss what is hydraulic radius and what is hydraulic depth. So it is basically a characteristic length that can be different. In fact, again for another problem or another study, what we call as a boundary layer, that length become different. So this length can vary from case to case, or depending on the problem we take different characteristic length, and thus mu is the dynamic viscosity of the flow. Well, that mu by rho is nu. What is kinematic viscosity? So this is kinematic viscosity. So ultimately this Reynolds number can be expressed as VL by nu, and for pipe flow, as I have explained, that this L can be diameter, and for open channel flow this can be radius, hydraulic radius or hydraulic depth. Now this term is used to express how much turbulent the flow is. Why? Because you can see that suppose you just consider that in a channel water is flowing with a velocity v. Now, in the same channel and then water is becoming turbulent there, water is becoming turbulent. Now, in the same channel with the same velocity, if you allow a oil to flow, if you allow a oil which is having say higher viscosity, and that with higher viscosity, a higher viscosity fluid, if you allow to flow, then you will find that turbulence may not occur in that particular fluid. So, this turbulence is inversely proportional to, we can call that it is to the viscosity term. And then similarly, if you allow it to flow with a very small channel, the same velocity, same fluid in a smaller channel, then your with a small hydraulic radius, what I mean, or with a small hydraulic depth, if you allow it to flow, then there may not be that much of turbulence. But the same velocity, but if it is flowing with a higher hydraulic depth, then you can find that the turbulence is increasing. So, again velocity is obviously, if other things remaining same, if the flow velocity is more, you can have more turbulence. So, that is why considering all these aspects, the Reynolds number is used as the index for indicating whether the flow is laminar or the flow is turbulent. And well, this expression we can get for pipe flow. For pipe flow, it is found that Reynolds number, if it is the Reynolds number up to 2000, when it is less than 2000, then the flow remain laminar. That is what established in the pipe. It was a lot of studies were conducted, and we can have these things, and you can visualize these things very well. In Reynolds apparatus, in fact, you can see these things. Well, in our lab class, we shall try to demonstrate that part also. Now, that say Reynolds number less than equal to 2000, and in pipe, what is that? We can write it is V d by nu, V d by nu. So, this should be less than equal to 2000. But this, in case of open channel flow, we use hydraulic radius. So, it should be represented by hydraulic radius. This d should be represented by hydraulic radius. Now, in case of pipe, if we write a hydraulic radius r, and if we just consider that it is a pipe, hydraulic radius is equal to A by P, just to refresh your memory. So, it is equal to area by perimeter, and in case of pipe, if we write these things, then it become say pi d square by 4 is the area, and then pi d is the perimeter of a pipe when it is flowing full. So, that we can see that r is equal to, we can just see that this is going out, and then it is becoming d by 4. So, hydraulic radius, if I just put the same expression of hydraulic radius in case of pipe, then we get an expression of d by 4. And we know that in pipe flow it is less than 2000. So, if I make it just V, then in place of d, if I write d by 4, let me put a 4 and nu is here. So, this will be, if I divide it by 4, this is becoming again, if I divide this 2000 by 4, then it is becoming 500. So, then d by 4 is nothing but we can replace this as r. So, what we can write that, well, let me write here, well, this part we can represent as r. So, V r by nu, which is the Reynolds number expression for the channel. So, V r by nu is less than 500, and from this just analytical concept also we can say that when Reynolds number less than 500, in case of open channel flow, the flow remain laminar. However, experimental study has shown that up to about 600 value, this flow remain laminar. Of course, it depends on some other factors also, like that, in fact, the viscosity will vary with temperature and all other factors, like that this is laminar. And then when the Reynolds number goes beyond 2000, then the flow become turbulent in case of open channel flow. Well, then when the Reynolds number is between 2000 and 500, then the flow is called in transition from laminar to turbulent. So that way also we can classify the flow based on its turbulence level. Well, then let me go to another classification, that is classification based on the concept of critical flow. Well, again, this what is critical flow and all that we will be discussing in more details about critical flow in our later part. But to start with, what is critical flow, to give you a brief idea, we need to have the concept of specific energy. We need to have the concept of specific energy. So what is specific energy? In our last class we did discuss that energy head at any section we write as, say if it is channel bed, then we can call this is as a depth y, and then say this is datum, we call z1 y1. Then if it is flowing with a velocity v, then there will be energy v square by twice z. So up to this much it is the energy. So we can write that energy at any level is equal to, say z1 plus y1 plus v1 square by twice z, 1 represented at the section 1. Okay. So this energy is per unit weight of fluid, that is why we call it as a energy head. And then if we measure this energy with respect to channel bed, that means our datum itself is becoming the channel bed. So we are talking about the energy per unit weight of flow with respect to channel bottom. So when we say that it is with respect to channel bottom, that means this z term is becoming 0. So our energy is becoming y1 plus v1 square by twice g. Of course, as we are saying about general without referring to a section, so we can write that y plus v square by twice c. And that energy we call as a specific energy. So when we say definition of specific energy, we call it the energy per unit weight of flow with respect to channel bottom, and this is nothing but E is equal to y plus v square by twice c. Well, now let me try to give you another concept. Say a water, some amount of water is flowing in a channel. Now let me just keep this expression that E is equal to y1 plus y plus v square by twice z, and in this channel amount of discharge q is flowing, and for this discharge, suppose in normal condition you have this much of depth y, okay, and then it is flowing with a velocity v. So it will have some energy, that will be y plus v square by twice c. Now suppose the same amount of discharge q is flowing and I have increased this channel slope. This channel slope here is suppose theta, and I have increased this channel slope like that. So this is theta 1. I have increased the channel slope. Now what will happen to the flow? The same amount of discharge is flowing, q is same. So definitely when you are increasing the slope, the flow velocity will increase, and when the water is moving fast, then the same amount of discharge is moving faster, so depth will become less, depth will come down, depth will come down. So now if I say it is y2, now I can again use index. Suppose in this case it is y1 v1, and here it is y2 and it is flowing with a velocity v2. So for the same amount of discharge, if I increase the slope, here the velocity become v2 and depth become y2, and for this it has energy, say E2 is equal to y2 plus v2 square by twice z, and for this it has energy E1 is equal to y1 plus v1 square by twice c. Now, is it possible to say, just concentrate on these two equations and these two relative value. Now, is it possible to say that whether E1 is more larger than E2 or say E2 is larger than E1? Is it possible? Because it is definitely not possible just by observing, because here these two terms are there, one is y1, y depth, another is velocity. Now, in this E1 this term is more than, that is y1 is more than y2, but the v1 is less than, v2, and here again v2 is more, v2 is larger, but y2 is less. So, we cannot definitely say that which one will be more, which one will be less. And then if we just change this slope, this energy level is changing, and for a particular slope we may have a situation for which we can have the minimum specific energy. That means, if I draw a graph, it will be like that. Say energy, if I plot in this side, and say depth, I am changing for the same discharge, I am changing the depth. Then this is a line, okay. Then I am plotting E versus Y, and then again one point, that is, as I am writing this energy versus Y, plotting this one energy versus Y. So, this is plus something, energy versus Y plus v square by twice g. So, if I plot E versus Y, a line, then say this is a 45-degree line, and it is always, we have a positive term, v square will always be a positive term. So, total energy will always be on the right side of this 45-degree line, because this line represents E equal to Y. So, something more than that means E is something more than this, means it will be always on the right side, and then if we draw a line, it will be like this. And you will find that with change of, say with change of depth, this energy is changing, and then for a particular value of y, you will be having a minimum energy, and this particular depth is called critical depth. Okay. And then another important point, for the critical depth, the Froude number, that also you know what is Froude number. So, Froude number is equal to, so v by velocity by root over g d, g to d, g gravity and d, and this is equal to 1. So, for critical condition, this Froude number become equal to 1. And so, this Froude number can be used as an index for classifying this sort of flow. So, when the flow depth is critical, then it is called as a critical flow, and when the flow depth is, suppose this is critical depth, that means when the water is flowing with this, I am writing YC critical depth, then your v square by z d term become 1, that is Froude number is equal to 1. Then when the depth of flow is less than this one, when the depth of flow is less than this one, say this is our critical flow depth YC, if the depth of flow is less than this one, then we call this as a supercritical flow. Now, in fact, generally the super terms comes when something more, but here when depth of flow is becoming less than critical depth, we are saying super. Why? Because basically we are naming it in terms of the velocity here. The velocity is more than the velocity of the critical flow. So, if I write it as velocity in critical flow, then this velocity will be more than that. So, that is why it is called supercritical flow. And then when we talk about subcritical flow, this depth will be, suppose it is critical depth yc, then this depth will be more than the critical depth. So, then it is called as a subcritical flow. Okay. And here again the velocity, basically the flow velocity is less than the critical velocity. If I write this as V1, this is V2, then what I can say that V1 is greater than Vc here, and if here the V2 is less than Vc. And of course, depth in terms of depth, if I write it as Y1, this is say Y2, then we can call here say Y1 is less than Yc, critical depth, and here it is Y2 is greater than Yc. But the many a time it get confused which one is sub, because sub generally refers to lower value. That is why suppose you may confuse that when it is Y1 is less than Yc, then it is sub, but it is not. Basically we are referring it, this suffix are coming, the prefix are coming because of this velocity concept. So, that way we again classify the flow as critical flow, supercritical flow and subcritical flow. Well, then another classification we have that we make in terms of whether we are visualizing the flow as one dimensional, two dimensional or three dimensional. Okay. This is particularly for analyzing the flow. So, for some case we can analyze the flow as one dimensional. Suppose in a very narrow channel, flow is occurring, and then velocity in the lateral direction, say it is a very narrow channel, you can refer to the slide, this say velocity in this narrow channel, say we are having this velocity flowing like this, and the component of this velocity, or suppose velocity in the lateral direction is very insignificant, neither in this direction, that direction, and maybe in the vertical direction also the change of velocity is not that significant, then we can call this as a one dimensional flow. So, what we will consider that flow is moving in one dimension, in one direction, that is called one dimensional flow. Now, in some case, suppose a flow is occurring in a wide valley, say in that case there may be significant component of velocity in both the direction. Let me give you one example. Suppose this is one river and there another sub channel is there which is also suppose a wider, or suppose there is an embankment and this has failed somehow and the river from water from this side has flown into that side. This also we can consider as open channel as it is flowing over the surface, and then here it will be moving like this, and in that case the flow direction V in this direction and other direction Vy, suppose these are also significant. Say if we call this is Vx, Vy, these are significant. So, we cannot neglect the flow in the other direction, lateral direction. So, that we call as a two dimensional flow. And similarly, in some cases the flow in the vertical direction, there may be some component of flow, a fluid we are considering here, suppose this I am considering here. So, it is moving suppose in this direction. So, there can be a vertical component of velocity and a component of velocity in this direction and in this direction, all the three direction it may have significant component of its velocity. So, in that case we refer this particular flow as three dimensional, and based on these consideration, that is basically we are visualizing. In real situation always the flow will be three dimensional, but considering the significance of the velocity in other direction or in all the dimensions directions, we can just classify it as one dimensional, two dimensional and three dimensional flow. Well, so what we could see that we have classified the flow based on different criteria, and of course we have just tried to see that how we can combine these classification to give a name to a particular type of flow. And in the next class we will move to another aspect, that here we have seen to some extent the flow velocity is not a single value. When the flow is occurring through a channel, it is not a single value. It is basically the flow value, velocity can be different at different part of the channel. Then in our computation work, how we will tackle this problem, how we make this sort of correction if we consider this as a single flow velocity. So that we will be discussing in the next class. Thank you very much. We hope we will be going in a better way in the next class.